All right. Good evening, mathematicians. Except for you guys, it'll be morning and afternoon. All right. In this video, I'm going to go over lesson 4.4 in Looking for Pythagoras. This is the final lesson in this unit, which means that after you complete this, your playlist is dedicated to reviewing for your test on Friday. So, well, let's just get right into it then. We're going to talk about these things that we call irrational numbers, and we've actually encountered them quite a few times already. Okay, so our focus question for this lesson here is, can you classify every number as either rational or irrational? Okay, now before we kind of get into classifying them, it's important that we kind of redefine all the other different types of numbers that are available to us, right? In terms of classifying numbers, in other words, giving numbers names, and that's what our vocabulary here is about. So, natural numbers, you guys might remember, are these are your counting numbers. Put simply here. So these are your counting numbers. For example, 1, 2, 3, 4, 5, and so on and so forth. Okay, so nice and easy. Those are what we call our natural numbers. The next set of numbers is what we call whole numbers. And whole numbers include your counting numbers. So we're going to write that again. So this is a set of numbers that includes our counting numbers, and it also includes 0. So for example, 0, 1, 2, 3, 4, and so on and so forth. Okay, so those are what we call our whole numbers. Now we have these things called integers. And you might have guessed, but this is these are our whole numbers, right? So all of our whole numbers, and their opposites. So for example, right, coming from negative infinity, I'll go negative 3, negative 2, negative 1. I include 0, and then I go to positive 1, positive 2, positive 3, all the way to positive infinity. So those are what we call integers. Now, here we arrive at this big umbrella term that we call rational numbers. And rational numbers are just numbers that can be written as a fraction. I believe that's the definition we have that we put previously in one of our previous lessons. So numbers that can be written as a fraction. So there we go. That can be written as a fraction. And then we're going to add to this, or a terminating / repeating decimal. Okay, so some examples would include the number 4. We could also do 3/4. That's a rational number. We could do 0.15. We call that a rational number because that's a terminating decimal, or a decimal that ends. And then we have something like this, 0.2 repeating. We also consider that a rational number because it's a repeating decimal. And then that brings us to our lovely term called irrational numbers. And you guys might be able to infer what its definition is. But irrational numbers are numbers that are non-repeating and non-terminating. So there's no pattern that repeats, and it also never ends. Some examples that we've encountered already include things like the square root of 2. Right? When you type that into your calculator, what comes out is a pretty complex decimal, right? And then actually it continues on even further. It continues on and on and on forever. Okay? So another square root example we could do, why don't we do the square root of 7? That's another irrational number because it creates this non-repeating and non-terminating decimal. And then another huge example would be the number pi. Right? Pi is also a decimal that is non-repeating and non-terminating. That's what makes these numbers irrational, or we call them irrational numbers. All right. And now we have the even bigger, gigantic umbrella term that we call real numbers. So real numbers is the set of all rational and irrational numbers. You might be asking, Mr. RG, if there are real numbers, then are there fake numbers? And my answer to that is yes, of course. You won't learn about these until probably high school, but we call them imaginary numbers. But don't worry about it. We're going to talk about only real numbers for today, okay? Specifically, rational versus irrational. Okay, let's continue. We have this, this is a really nice graphic here, okay? So I said that real numbers was a gigantic umbrella term, right? If I were to try to draw an umbrella, let's see if I can do this. There we go. Okay, that is somewhat that somewhat resembles an umbrella. Sorry. Okay, but anyway, so think of the real numbers as a giant umbrella, and all of these things in these circles underneath fall into that umbrella term, real numbers. Rational numbers are real numbers. Irrational numbers are real numbers. Integers are real numbers. Whole numbers are real numbers. And natural numbers are real numbers. I'm going to erase my umbrella because I'm very ashamed of it. So, my umbrella, sorry, but you get the picture here. Okay, so real numbers is the big umbrella term that holds all of these other terms. You'll also notice that, let's take natural numbers for example. Natural numbers are considered whole numbers, but not all whole numbers are considered natural numbers. Interesting. You'll notice that whole numbers are considered integers, but not all integers are whole numbers. You see what's happening here? So as you go smaller and smaller into these circles, right, you're getting more specific. And then as you go outwards, you're getting a little bit more general, okay? You're casting a wider net here. But natural numbers are whole numbers are integers are rational numbers, and rational numbers are real numbers. Okay, so we have different types of square roots, right? We've been working with square roots for a little while now. We have rational square roots. We have irrational square roots. Some rational square root examples I can think of. The square root of 64 gives me 8. That is 8 a rational number? Yes, it is. Let's try this one. What is the square root of 0.25? Well, that is just 0.5. 0.5 is a terminating decimal, so therefore it is a rational number. See if you guys can come up with 2 more examples of rational square roots. All right. Irrational square roots. So remember, irrational means that you are non-terminating, I'll abbreviate it here, non-terminating, and you are non-repeating. So the first one that pops into my brain is the square root of 2. And the square root of 2, I don't remember what it is approximately. I think it's like 1.4 something. Here, let's do square root of 2. Yeah, 1.414. So 1.414213. 1.414213 ... Another example I can think of is the square root of 3. So let me type in here. Square root of 3 is 1.732050. 1.732050. And that continues on forever and does not repeat and does not terminate. All right, come up with, let's do one more example of an irrational square root, okay? Alrighty. So, question A, it says write 3 or more non-terminating, non-repeating, underline those please, non-terminating, non-repeating decimals that are greater than 0.5 but less than 0.6. So it has to be within this range here. So think about this one for a second. Come up with 3 or more examples. Okay. All right. So in my brain, I'm thinking, well, in order to be greater than 5 but less than, in order to be greater than 0.5 and less than 0.6, really all I need to do is just add a bunch of decimals after this 5 here. So I could go 0.5263791162113. And I say that continues on forever. Is that irrational? I would say so. It's non-terminating, non-repeating, because honestly, there are numbers, I'm going to say that there are numbers past this 3 that I just wrote. Okay? Another example I can think of off the top of my head, 0.5991327, 264134, and I'm going to say that continues on forever because it needs to be non-terminating. All right, last one, 0.5831695995692, and again, it continues on. Now, question number 2 is asking us, well, why is there no limit to the number of non-terminating and non-repeating decimals that are between 0.5 and 0.6? Now, try to answer this one on your own. Really think about it, and I hope you guys come up with what I'm thinking as well. So, why is there no limit to the number of these non-terminating and non-repeating decimals that are between 0.5 and 0.6? All right, let's talk about it. So, if you think about it, you probably came up with a bunch of different examples that answer question 1. So honestly, I feel like the reason why there is no limit is because there's really an infinite number of combinations that you can do. There is an infinite number of combinations. And then we'll add between 0.5 and 0.6. And there we go. All right, making some headway here. Let's continue. Okay, so as a refresher, this symbol means greater than, more than, no less than, and then this symbol is our less than or no more than. Okay, so question B is asking us to write different number approximations or estimates here. But let's go ahead and write the exact value for the square root of 5. So let me type that in here. Square root of 5. Whoops, that's square root of 35. There we go. 2.236067. 2.36067. I already forgot it. I was doing so well. 236067. 236. Whoops. 236067, and that continues on forever. So, question number 1 wants us to write a rational number estimate for the square root of 5 that is less than the square root of 5 and one that is greater than. So, a rational number that is greater than the square root of 5. Think about this for a second, write an answer, and then we'll compare. All right, hopefully you paused it, and hopefully you wrote something. In my brain, I'm thinking, well, I know that the square root of 5 is approximately 2.23, so if I round that number to a 4, then I have myself 2.24, which is greater than the square root of 5, but it's also a rational number because 2.24 definitely ends. All right. And then for a value below the square root of 5 or less than the square root of 5, I could say 2.22. Right? Because if I square 2.22, that's definitely less than 5. Yeah, that works. Okay. And there we go. All right. Next one. It says write an irrational number estimate for the square root of 5 that is less than the square root of 5 and one that is greater than the square root of 5. Remember, irrational means that this is non-terminating. Going to abbreviate that here. And non-repeating. So, I need an irrational number that is greater than the square root of 5. So I know that the square root of 5 is 2.236067, so I'm just going to slightly change one of these numbers so that way it is greater than. So 2.246321167.9, and that repeats on forever and ever. So that one's greater than the square root of 5. We need an irrational number that's less than, so I can maybe take my rational number estimate and then do some, I don't know, maybe like 1,967,3,2,8,4, and say that continues on forever. And there we have some nice irrational estimates. Okay, let us continue on to our last page here. So the directions say to tell whether each number is rational or irrational, and to explain your reasoning. I'm going to walk through maybe 2 of these with you guys. Okay, then I expect you guys to finish off the rest on your own. Okay, so to save your hands from cramping, you can abbreviate rational as R. Okay, and irrational, we're not going to use I because I is something else in math, so we're just going to say IR for irrational. Okay, so let's take the square root of 7. Well, the square root of 7 falls in between the square root of 9 and the square root of 4, right? It's definitely not a perfect square, so we're definitely not going to get a nice whole number as our answer. So automatically, my brain is saying, hey, this is an irrational number. And what makes a number irrational? Well, it's a decimal that is non-repeating. So I'm going to write this fully here. It's non-repeating and it's non-terminating. And there we go. So this part is the explain your reasoning. This part is the irrational or rational. All right, let's take a look. Number 2, the square root of 16 equals 4. Well, is 4 a rational number or an irrational number? Hopefully you said rational number. And then we need to explain our reasoning. Well, 4 is, technically it terminates, right? So we'll say that this terminates. It's a number that terminates. It's also a number you can write as a fraction. It's also a whole number. It's also it's all of those things, right? All right, number 3. Last one that I'm doing with you guys. Square root of 4 times the square root of 4. I know that the square root of 4 is 2, so this is really like 2 times 2, and 2 times 2 equals 4. And 4, again, is rational, and this is a number that terminates. Alright, kiddos, I feel like you guys can take the wheel from here. So answer questions 4 through 12. Classify each of these numbers as irrational or rational, and then tell me, how do you know? What makes it rational? What makes it irrational? Alright, you guys got this. Alright, I will see you in the next lesson.